So let me start by asking a question. How many of you have heard of covering arrays? Okay. How many of you use covering arrays? Once, right? Okay. So what I'm proposing to do today is not just talk about covering arrays, but talk about how covering arrays are used, right? And in particular, I'll focus on how covering arrays are used for validating software. Hence the title, Covering Arrays and Software Testing. And so what I'm going to do is I'm going to start by framing the conversation a little bit. I'll set the stage, right? I'll talk about the software testing dilemma. And then I'll hopefully persuade you that covering arrays as a construct can be useful in addressing the so-called software testing dilemma. So we'll get into the weeds a little bit, right? But not too much into the weeds. I will also present a series of examples that I hope will illustrate the utility of covering arrays. And then, since it's a small group, hopefully we'll have some back and forth, and I'm willing to take questions during the presentation. So if I'm too far down in the weeds or too high up, let me know, and I can always get deeper in the weeds if you want me to, right? So when did I get interested in covering arrays? Well, let me say a little bit about my background before I start. So my background is in software engineering. My PhD work was in software reliability theory. And many years ago, I went to a conference, and at that conference, a paper was being presented that was co-authored by a statistician that many of you may have heard of. His name is Colin Mallows, right? Well known for the CP statistic. He wrote a paper with his colleagues at Bell Labs and advocated the use of covering arrays for software testing, right? The paper eventually appeared in Technometrics, right? And this is in 1998, the paper appeared, right, in Technometrics. And he proposed a term that has not stuck, right? He proposed the term factor covering design to describe these constructs. So I'm not going to use that term. I'm going to use covering arrays. If you've heard of factor covering designs, it's the same thing, right? I was at that conference, and I thought this was totally uninteresting, right? I thought that the only avenue worth investigating as a software engineer interested in validating software was software reliability theory. How wrong was I, right? And many years later, about 8 years ago, I realized that this was far more useful and interesting than I realized all the way back in 1997, right? And so I'm going to share a little bit of what these constructs are all about. So let me start by motivating the conversation, right? And I'll sort of motivate it by bringing to your attention a few little details that appeared in a NIST report back in 2002, some 12 years ago, and in a paper that appeared in 2002 in the IBM Systems Journal. And the paper that appeared in the IBM Systems Journal was by the Heilpern and Santhanam, right? And they were talking about software testing. And one of the things that they claimed in that paper was that up to 75% of the resources, the cost of building software, could be attributed to software testing activities, right? So today, it's not uncommon for you to hear about software projects that run up costs of $100 million, right? So think of what we're talking about here. We're talking about big numbers, right? Now, NIST, at about the same time, were investigating this issue of what is the impact of software failures to the economy, right? When software fails, whether it be, and we're not talking here now about the types of failures that lead to loss of human life, right? We're talking about outages, right, that result in a business losing money, right? And their estimate, and we're not going to get into the details of how they quantify these numbers, is that the impact on the economy, this is 12 years ago, was somewhere around up to $60 billion, right? So rather serious. Now, let's fast forward a few years. In 2006, at the SAS Institute workshop on covering arrays, a gentleman by the name of Alan Hartman from IBM Research, who is in some sense an iconic figure in the covering arrays research community, right, presented a talk where he said that the cost of outages, right, is quite significant and really significant for certain types of businesses. So if you think of a brokerage operation, right, the hourly downtime cost due to a software outage could be around $6 million. And so he ranked them in this way. So the point I think that Alan Hartman was trying to make is that software testing is important, right? Testing is expensive. Why is it expensive? It's 50 to 75% of the cost of a software development project. And he says poor testing or inadequate testing is even more expensive. Why? Because you discover the failures when the software is released, and certainly if the software fails and leads to loss of human life, then we're talking about really serious costs, right? So what do you do, right? So it's not surprising that software testing practitioners are faced with this sort of dilemma, right? You need to improve quality, but software testing practitioners are always faced with the challenge of doing it in an abbreviated time span. They rarely have enough time to validate the software. The expectation is that they need to find all the bugs that exist, and often people are asking them, are you done yet? Did you find everything that's likely to lead to a failure, right? And so this conundrum, you can think of this as the simultaneous optimization type problem, right? We want to minimize test set size because that impacts cost. The smaller the size of the test suites, the cheaper it is to test. But at the same time, you want to maximize what I term fault detection effectiveness, right? And if you want to know more about fault detection effectiveness, that's a topic that is very prevalent in the software engineering research community, and we can talk more about that later. Okay, so when you think of this sort of conundrum, right, and you think of it for a little while, you begin to imagine that this conundrum is not unlike the type of situation that people who turn to design of experiments as a discipline, right, it's not unlike that type of problem that they face, right? And fact of the matter is that for a long time, software engineers, software developers, software practitioners have realized that this is one way of looking at this conundrum. So if you look at what I have cited as the milestones, you can see all the way back in 1985, right, orthogonal Latin squares were being proposed as a way to validate compilers, right? Now, how many of you have heard of the programming language Ada? Mandel, in 1985, in the communications of the ACM, proposed orthogonal Latin squares to validate the Ada compiler, right? And that's not very well known, but this is the sort of thing that has been going on for years. And a few years later, Brownlee proposed orthogonal arrays. And in 1998, Dalal and Mallow's famous technometrics paper appeared, right? And that's the first time in the literature that covering arrays came into being as a construct that could be associated with validating software. Okay, so what is a covering array? So let me get a little bit into the weeds with a definition, right? So a covering array is really a very simple construct, right? And so I'm going to propose a few things with this definition. Some notation that I'm going to use throughout, right? And then I'm going to explain what the notation means, right? So notice the notation that I'm using there, right? It's this CA parentheses N TKV, right? You can think of the T, K, and V as the specification of the covering array. Let me talk about what those things are. And a covering array is nothing but an N by K array. N rows and K columns, right? But it has certain properties, right? And so the properties are these. First thing we have to consider is that if you take the ith column, right, then it has V distinct symbols, right? That's where the V comes from in the specification. Maybe 2 or 3 or 4, whatever, right? And most importantly, if you take a T coordinate projection of this array, what do I mean by that? If you take any T columns and you extract them from the array and you examine their contents, right? Then remember that every column has V symbols. Let's take a T coordinate projection, right? Then if you think of the combinations of the symbols, then you have V to the T combinations, right? And the important thing here is that all V to the T combinations of symbols exist at least once. They may exist twice, 3 times, but you must have at least one occurrence of those combinations for each combination. And if you do, it's called a covering array, right? It is that notion of coverage, right? It exists at least once that leads to the term covering, right? And so if indeed that happens, you have what is called a T covering array, and some people refer to it as a strength T covering array, right? Now, T can be any number greater than 1, but typically it's a number greater than 2, right? And I'll explain why there is that sort of subtle distinction. Now, it's optimal if n is the smallest possible n for the specification given. Simple idea, right? Let's look at some basic examples.
So the distinction between an orthogonal and
coming to that. Nice. Coming to that, right? Just stick that point, right? Right. Okay. So let me just illustrate what I just said with some examples, and then I'll connect it to orthogonal arrays. Okay? All right. So here are 2 examples. Right? What I have here are examples of 2 covering arrays. So if you look at the specification for these, on the one on the left, right, we have a 6x5 array, right? 5 columns. If you look at it, you'll see that each column has 2 symbols, 1 and 2, right? And so what I claim here is that if you take, for the one on the left, any 2 columns, all possible combinations of the symbols exist. How many combinations are there? 4, because it only has 2 symbols for each column, right? And so there are 5 columns. I'm taking 2 coordinate projections. There are 5 choose 2, right? So I can sit here for a few moments and you can go through all 10, but trust me, they all exist, right? Similarly, if you look at the one on the right, right, we have 5 columns, but this one has 12 rows. And what I'm arguing here is that it's a strength 3 covering array, because if you take any 3 columns, all possible combinations of symbols exist. And there are 8 combinations because each column has 2. So let us look at an example. Let's take those 2. You should find 1, 1, 1, 2, 2, 1, and 2, 2, right? Let's take those 2. We should also find those combinations of symbols. And we could do that for all 10, right? If we take those 3 columns, you should find all 8 combinations of the 2 symbols, right? And if you take those 3, we should find the same thing. And there are only 5 3-coordinate projections there. And so the question is this: are these optimal? Because we're always interested in those things, right? We're interested in making these things as small as possible because that's fun, right? But if we think about it, I'm going to project a little bit. For a software tester who is worried about budget, making it as small as possible makes sense. And we're going to sort of make that argument a little bit more persuasively in a few minutes, right? And the answer, are these optimal, is the one on the left is optimal. There's no way you can make it smaller than 6, but the one on the right is not, right? As it turns out, the one on the right can be constructed in 10 runs, right? But I won't show you an example of that. Okay, orthogonal arrays now, right? So before I get to orthogonal arrays, any questions about that?
Yeah.
Yeah.
So you said for the ith column has V distinct symbols.
Right.
So if you have, take the small one.
Yeah.
You say CA6252, so the V is 2.
Yes.
So you said there's only 2 unique symbols in that column?
Yeah.
Okay, so what's T then?
That's the number of columns you're examining at each point in time.
Oh, so it's like,
So it's a t-coordinate projection, which is why my arrows are pointing to 2 columns at a time for the one on the left. For the one on the right, I have 3 arrows.
columns, is that?
Say that again?
So you're going to select those columns
And project them, examine them, look at the level combinations that exist.
do you have to choose every single?
Yes. Otherwise, it's not covering.
combination of
Yes.
2 columns?
It's 5 choose 2.
Right.
Right. Does that make sense now?
Yeah, so why do you do that?
Well, we are going to connect it to testing in a minute. Right. Right.
How would you construct an array like this? So you have 2 symbols. Bring it down to like application level. So what are these columns represent in your software? What do
Okay.
those represent?
I'm going to connect it to testing in a minute. Just give me a second, right? And I'm going to show you a very simple example, right? And you're going to see what I mean.
Okay.
Right? So just hold on to that point for a little bit. Right? So at this point, all I'm doing is talking about an abstract construct. Right? Discrete mathematicians don't care about applications, right? They just love to play with symbols, right? Is there a discrete mathematician in the room? So that's an area of my research as well. So I'm guilty as charged, right? When someone said, well, why do you do this? I was stunned, because it's fun. Right. So just give me a minute, right? Let me get to an example, and then you may either have your question answered, or you may have some other questions. It's just 2 slides away, right? Okay. All right. Okay, so let me address the orthogonal array issue. Okay, so here's a definition that is worth mentioning at this point, partly because the question of orthogonal arrays was raised. So let's say we have a covering array, right? Now, if for any t coordinate projection, right, the vt to the t combinations of symbols exist exactly lambda times, then it is an orthogonal array, right? In fact, it's a t-covering orthogonal array. And what is important here to recognize is if you've ever heard of covering orthogonal arrays in your statistics classes or whatever it may be, you are really just studying a very special type of covering array, right? And I have a book here, but it's being used for a very important process. But it is a famous book on orthogonal arrays, right? Publisher is Springer Books in Statistics by Hadayat, right? On orthogonal arrays that every design of experiments person has under their arm as they're walking around thinking about design of experiments, right? Orthogonal arrays is just a special type of covering array. Covering array is a more general construct. Orthogonal array is a very special construct. And there are reasons why the exactly lambda times make it particularly useful for statisticians, but we're not talking about why this stuff is important for statisticians right now, right? It has to do with things like estimability and so on. You need replicates and so on, right? Okay. So another important construct that I want to look at, right, before I get to your question in a couple of slides, right, is this notion that you will see as I go through this, and it's the idea of the covering array number. This is a simple idea. It's the size of the covering array, right? And so that's what that definition tells you. All right? So I'm going to talk about size in a little bit more detail as we go on. But here's a little deeper dive into the weeds here, right? Because we have to show some stuff in the weeds, right? I want you to just think about this for a little bit. We're interested in size. I'm going to sort of make the argument that the size of a covering array is an important thing if you're thinking of budget and software testing, right? But I want you to recognize that there's this notion of lower bounds, right, on the size of these constructs, right? And it should be obvious to everyone that the lower bound on any covering array is just v to the t, right? It can't be smaller, otherwise it can't be covering, right? It's important to remember that, because I've had no end of conversations with people who claim they're using covering arrays, and they're excited that they're using a covering array of size n, and the lower bound is m, which is greater than n. So they're using something, but it's not a covering array, right? So, be warned, right? You may use some tool to construct what you think is a covering array, right? And if it is not, it's not buying you what you think it's buying you, right? So important lower bound. The other thing is if you increase the number of columns in this array, then the size is going to monotonically increase. Right? If you increase the number of levels, it must also increase. So if somebody increases the number of factors and the size goes down, then that's troubling, right? And that will happen, right? Okay. All right. So another point I want to make is this one. What some people find quite astonishing is that if you think of the specification of a covering array, right? Values, settings of t, k, and v. These are integers, right? They can range, you can have thousands of columns, many levels, many strengths, right? The only specification that has been solved, right, is a case where t is equal to 2 and v is equal to 2. Binary covering arrays of strength 2, right? That's the only problem that people can say definitively, that I can construct a covering array of this number of factors, and this is the size. In general, people don't know how small they are, right? In general. Right. You may know the answer for certain settings of k, right? When v is 3 or t is 3, but you haven't solved it for all k. Nobody has solved it for all k. So, for those of you is there anyone who is a student in grad school now? No?
Just finished.
Just finished? So if you go back, right, here is a rich opportunity to solve problems that are important to people. No, you're not going back. Right? Big open problems, right? Some of the most well-known scholars in the covering array community, right, have written really voluminous numbers of papers on the covering array number for small numbers of factors, right? And these are very important papers in the literature. Charles Coburn, for example, is a name that you will hear from Arizona State that has done a lot of work in this area. Okay, so that's deep into the weeds. Let me pop out of the weeds a little bit and try to address your question.
More like clouds than weeds.
Right? It's too high up?
Yeah, I'm still grasping for like, how would I use it?
Right, okay. So I'm gonna try and answer your question, right? So I'm gonna try and connect covering arrays to software testing here. And I'm gonna look at what I'm gonna propose here is a very simple, almost trivially simple software system. Foo, right? Surely you've heard of Foo, right? Foo is a generic system that everybody talks about, right? And my Foo has 4 arguments. Think of it as a function. Just 4 inputs, right? And what is more, each of those inputs can only have 2 values. Does that make sense? Right? So I have a simple function, 4 input arguments. Each argument can be 1 or 2, 0 or 1, 2 values. It does some stuff. Right?
So like if I went through the wizard, there'd be 4 steps, and each step would be, do you want option A on or off, option B on or off, option C
right.
on or off.
You can think, you can think, in fact, I'll show you, when I show this example, Melinda will say, oh no, right, why did he show that example? So think of a dialog box, right? It's prevalent in software systems, and you're setting some preference, and there are 4 check boxes, right? You check them, you click OK. What the hell is it doing? Right? It's doing something, right? Right? It's doing something. So simple software system. What I'm saying here is that the input space, right, is fully defined by that construct on the right. Right? Those are all the possible inputs, valid inputs. Right? And so, what does a software tester do when they're faced with validating this trivially simple piece of software? They say, I need to come up with expected results for each of these settings. I need to exercise the software on each input. I need to compare my actual to my expected. And if there's any difference, the programmer has to fix it. Right? But there are 16. Right? So what are these things? Right? If m is equal to 2 and n is less than 3, do this, right? Is that beginning to answer your question?
Well,
right?
yeah, so but really what you would do is you would say all of these combinations need to be tested.
Oh, for sure. Well, that's what some people say, right? But let me just suggest this to you, right? This is trivial. It's 4 inputs. The input space can be fully defined and shown on one screen, right? And you may say, oh, that's easy. We'll just, exhaustive testing is all we need to do. Well, what if you're testing something, right, where the cost to test each of these is not thousands of dollars, but perhaps millions of dollars, right? And you have a budget. You may only have $3 million, right? But it costs $1 million to test each one. Which 3 are you going to do? Right? And so that's the question I'm going to try and answer. Is that beginning to make it more concrete to you, right? So is this now in the weeds where you like to be? Yeah?
Well, it's
attached to something, right? Right, okay, okay. So is that clear? Am I making sense here? Okay.
So you're going to basically show me a way to cut down on the 16 combinations using covering rate.
Exactly.
To prove that we've got to.
Well, I may not do any proofs, right? I'll give you, if you're interested in the proof.
Engineering.
Right. Oh, engineering proof. Right. 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 Okay. Right. I'm going to try to convince you by using a principled argument that the reduction in number, right, is a reduction that you may be satisfied to live with. Right. Is that sort of acceptable to you, you think? Yeah. Okay. All right. So the question I pose here is a question that all software testers face. I know what the input space is. I know that exhaustive testing is something that I'd like to do, right? That would be ideal. But what if I don't have the budget for exhaustive testing? What if I can only test 8 things, right? So what are we talking about here then? We're talking about a sampling strategy from the input space, right? That is a sampling strategy that allows me to have some degree of confidence that I have the highest probability of identifying defects. Yeah? Okay. So let's go through this exercise a little bit more detail. So that's the input space. So one strategy is random testing, right? I could say I have a budget of 8. I'll just randomly pick 8 things. Right? Here's one random choice. What's wrong with this choice? Right? I've only tested the conditions where M is checked or unchecked. And it may crash when M is the opposite.
You get a lot of information.
Right. I've used up my testing budget. Right? But it would be, am I?
To reattaching.
No. Am I still recording adequately? Okay.
Sorry about that. Go ahead.
Right. So here's a strategy that, by the way, right, I should point out that random testing is a strategy that many people use in the real world, right? And there are lots of papers that people write about the usefulness, right, of random testing as a testing strategy. Here's a strategy that is much weaker than this, right? And this is commonplace. There are testing organizations that follow the strategy I'm about to describe, right? And they are considered to be principled testing organizations. It's called all values testing, right? Lots of people who write software, their standard is that we should do all values testing. Well, I can do all values testing in 2 runs. One testing scenario, all 1s, and one testing scenario, all 2s. What's the problem with that? Big problem, right? Okay. All right. I think we should use this strategy. Those are the 8 that I want to pick. How did I pick those? My covering array algorithm picked it. And what does it do? It says I need to build a testing scenario, right? And I need to sample from the input space in such a way, right, that I satisfy some criterion. And the criterion is simply this. I want to sample from the input space so that if I take any 3 columns, all combinations are there, right? And I know that when I do that, my lower bound is 8, and it turns out I can assemble these things in such a way that the total size of my covering array is also 8, right? So what have I done? I have satisfied all values testing. I have ensured that all possible interactions of 2 factors are covered. All possible 3-way interactions are covered. And 50% of the 4-way interactions are covered. Why is this useful, right?
Because unless it just so happens that there's some wonky setting of all 4 that didn't fall into 50% of the check, you've got all the combinations that are likely to make everything fall apart.
So let me say a little bit more, right, about software and testing theory. The people at NIST, there are 2 scientists at NIST who do a lot of work. National Institute of Standards and Technology is the acronym NIST, Kuhn and Kacker. And they've done extensive experiments on this. And what you've discovered, right, is that software failures are often due to interactions of values of fewer than 6 factors. Rarely do you see failures precipitated, right, by more than 6 inputs. Right? There's this saying in testing that bugs congregate in corners or lurk in corners and congregate at edges. Have you heard that one? Right? Well, it's been around for years, right? What that means is the interactions that matter, the edge cases that matter, right? And the empirical research has shown that you rarely find bugs due to more than 6-way interactions. And in fact, 2-way interactions often, depending on the type of software, is good enough. What we've done here is we have 3-way. And as you said, Dan, in that weird scenario where it's due to 4, we are good. So of course, what does a testing manager discover after the testing manager comes up with this grand idea, goes to management and says, oh, I can do it in 8. They say, you know what, you only have time to do 5, right? So what are they going to do now, right? Here's a solution. They're going to use that one, right? And why is that one good? Because it's 2 covering. And what's more, I can say that 63% of the 3-way interactions are covered. So what I think I'm doing here is making an argument, right? You can think of this as, you know, exhaustive testing is a holy grail, one could argue, but it's often impractical, right? So is there some pseudo-exhaustive testing mechanism that we can use, embrace, right? By which I mean, can we come up with a testing strategy that is almost as good as exhaustive testing, but at dramatically less cost? Right? Can I come up with a strategy to sample from the input space, right, in such a way that I satisfy some objective criterion, that when I'm done and that someone comes to me and says, are you done yet? I can say, look, I need to test 5. I've only done 4. I've done 80% of the testing that I'm doing, that I need to do, right? And if you allow me to do 1 more, I can assure you that any fault due to 2-way interactions, I have examined, and I can assert that they do not exist. That make sense? Okay, all right. So I'm going to show you an example now. Kacker. No, not Tucker. Okay. That's, you're thinking of linear programming, right? I'll show you the reference in a minute. So that was a sort of silly example, foo, right? There's no such software system called foo, and if there is, I would be a little bit concerned, right? Here is a system that's real. Colin Mallows talks about it in his technometrics paper, right? We're talking about air-to-ground missile system, software that controls the avionics, right? Okay. 10 inputs. It's tracking things like wind velocity, pressure, and the like, right? So one thing you should notice here is This is a little bit different, not just by numbers of factors from the previous example I showed you, where that was discrete values, right? Now we have continuous values. And you're saying, what are we going to do now? Right. Can you imagine exhaustive coverage here? Right? But guess what? Testers know how to handle continuous factors, right? They have known about this for years and years and years. The strategy that you would use is equivalence partitioning and boundary value analysis, and they know about that stuff. And if you haven't heard about equivalence partitioning, right, or boundary value analysis, it's a simple idea. Go to your discrete math class, where they spoke about equivalence classes, partition your input space into equivalence classes, select a value from each equivalence class. Boundary value analysis merely says, pick values at the edges, edge cases, right? So what Colin Mallows said here was, this one is easy, right? We know what the range of values is. We'll take the lowest and the highest. And if you really get bent out of shape because I'm only picking 2, I'll pick the one in the middle. So I've gone from continuous to discrete valued, 2 or 3, right? Happy with that? Anybody worried about that? You shouldn't be. This is a principled practice in testing. Okay. All right. But guess what? Still expensive. Look at this. 10 factors, 2 values, over 1,000 test cases for exhaustive testing. Right? Can you imagine? We're talking about the missile system here. How do you test this stuff? You fire this thing off and it blows up. They cost $1 million each. Right? And the cheap ones cost $100,000 each. Right? So even 1,000 is expensive. And that person who said, can't do 2, gotta do 3, 59,000 test cases for exhaustive testing. What are we going to do now? All right? Okay. Can covering arrays help? Are you surprised that I said yes? Okay. Right. Let me just do a quick demo, right? So what are we going to do? I'm going to just do the case where, I'm burning a lot of time here. I'm not sure how.
We have the room until 8:30.
Right.
We'll probably wrap up around 8-ish.
8-ish, okay. I'll try to do that.
If everybody's deep into the debate.
Okay, so let me so I'm going to address, so what I'm using here is Platform and Jump. Jump is a division at SAS that Linda and I work for, right? Never heard of it, I'm sure, but it's a and what I'm going to do is, it's 10 factors, right? 2 levels each, all right? Okay? And so the question is, given that exhaustive testing would require over 1,000 test cases, right? Can I come up with a set of test cases that will give me some confidence that I've done adequate testing but using fewer than 1,000, right? That's a good challenge. And so, without further ado, we can use 6 test cases, right? And I would argue here, right, that a testing manager who has to validate this air-to-missile software system, right, can use just 6 test cases and assert, right, that when they're done, that not only, right, have they ensured that all 2 coordinate projections, all 2 factors, they have validated, they can verify that the software will not fail due to 2 factor projections. What they can also say, what this report is showing you, is 68.75% of 3-way interactions are tested, right? And 37% of 4-way interactions are tested. And if you have reason to believe that for this software system, faults are due to two-way interactions, you can say that you're done, right? 6 runs. Not 6. 6. 6 runs, right? So if the budget is substantially less than 1,000, the testing manager can propose this and then make an argument of, well, how much more budget can I get? And I can perhaps ensure that not 68.75% of three-way interactions, but 100% of three-way interactions are done. And in fact, I can do that now. I can just go back. I can say I want strength 3. I can continue. I can make the table. 13. All right? That makes sense?
Yeah. And so what you said earlier about it monotonically increasing,
yeah.
Does that mean that your two-factor with a 5-run, 6-run coverage is a subset of that?
No, not well. No, not necessarily. As it turns out, we can talk about this a little bit. But when you remember, I showed you a table, right? That I said was solved, and there were ranges of values, right? And you knew that for certain numbers of factors, they're all 6 runs, right? Then if it's in that range, it's just a subset. So we can go back to that, right? So does that make sense? Right? The air-to-ground missile system? Okay, let's get back to the presentation here. Okay, so, yeah.
So, by using that algorithm, you can spit out the exact test cases that you need?
Yes, those are the test cases.
A lot of times, the different parameters have different numbers of symbols.
Which is what we're doing right here now. I anticipated your question and I brought up the slide just in time, right? I knew you were going to ask that. So guess what? Life is not so easy, right? All the factors don't have the same number of levels, right? And that's what this definition is all about. There is this construct known as a mixed level covering array, in which case each column can have a different number of levels. And we also want to handle that case. Make sense? And here is an example of a mixed level covering array. 5 factors, 2 have 3 levels, the remainder have 2 levels, and guess what? It's optimal. Why is it optimal? Why is it an optimal 2 covering array? By the definition, the smallest it can be. Product of 3, 9, right? Okay? So that's your answer. Right? You do have mixed level covering arrays. And now I'm going to get to a very important problem that is pervasive in the literature. Right? This is a very serious problem, right? It has to do with a traffic collision avoidance system. Anybody know what that is? Anybody fly on planes? Right? Air traffic, well, it's not air traffic control, right? But similar. So if you fly on a plane, you have been in touch indirectly with software that keeps you safe, right? So let's describe what that is. Before I do, let me talk about some civil aviation incidents. Right, so in 1986, there was mid-air collision over California, Aeromexico DC-9, and a private plane, right? 82 deaths. Precipitated Congress to act, right? Mandated that all passenger planes over a certain weight must carry the system of software and hardware that allows the planes in the air to know where each other are and provide warnings to the pilots to avoid mid-air collisions, right? 1996, New Delhi, 349 deaths, right? India acts immediately. India now requires all passenger planes flying into Indian airspace to have traffic collision avoidance systems. Germany, 2002, right? Mid-air collision. Tupolev and DHL Boeing 757, 71 deaths. They had a TCAS, but the Tupolev pilot ignored what the TCAS system told him to do, right? So Germany imposed a stricter regime on air traffic, on the TCAS system. Brazil, 2006. You probably heard about this on the news, right? A Legacy 600 is flying up to New York. Private jet. These planes are built in Brazil, widely used in the aviation industry. It's flying along, mid-air collision with a 737. Everybody on the 737 dies, right? The Legacy 600 lands and the pilots live, right? Now you would think the other way around, right? What happened here? They both had TCAS. One of them was off, turned off, right? So it resulted in the Brazilian government saying, look, we have to up the ante on the regulations, right? So that these things are used in our airspace. Every civil aviation authority across the world requires passenger jets of a certain size to use TCAS, right? And so what is TCAS? What TCAS essentially is, it provides protection envelopes around planes, right? And it issues two things, what is called a resolution advisory or a traffic advisory. So you can think of these envelopes within envelopes, right? Tiered envelopes, right? Where if there are planes within the wider envelope, there is a signal on the instruments in the plane which says, there is traffic. Be alert, right? If it's in the inner envelope, it says, look, you need to do this, climb or go down. You don't think, you do, right? And if it's in the red, well, not good, right? Okay. Does that make sense? All right. So what is it? It's a system, it's a computer system with sensors, right? Okay. So that's the schematic, right? This diagram, by the way, you can go read this stuff. Go to FAA's website, and you can download the manual. It's in wonderful light reading, right? If you want to read this stuff, right? Okay. And we're going to focus on the computer unit, right? Okay. The software is not that complicated. It's just a few hundred lines of code, right? But it does a very important thing. And it has 12 inputs. And I'm not going to describe what all of them are, but suffice it to say some of them are self-evident, right? So if you look at number 7, for example, what the FAA has done is it has stratified airspace into tiers. There are actually 4 levels. And number 7 is saying what level is a plane in, right? And so it tracks things like the separation between the plane upwards, plane downwards, and other things. Okay. So without getting into all the details, let us just focus on the settings. Again, some of these things are continuous values, but let us assume that they have been discretized, right? And these are the discretized settings. So you can think of this specification as a specification that you may want to use here, right? And so what we want to do is construct a mixed covering array where there are 2 factors of 10 levels. That would be numbers 8 and 9, right? 1 factor of 4 level, that would be number 7. 2 factors of 3, and the remainder 2, right? So if you think about this, if you do the math, I did this just before coming here. If you take the product, if you think of exhaustive testing, there are 460,800 test cases. How do you think they're going to test this? They're going to send the planes up, right? They're going to try and make sure that they trigger all of these things. And I did the math. And if you assume that they can test 5 scenarios per hour, then it's 92,000 hours, approximately 10.5 years to test the software, right? And I looked up what it cost. We have, SAS has a fleet of jets, and I went and checked how much it cost per hour, right? And I don't know if I should say, but let us say it's about $10,000 per hour for a 737 or a 757, You can do the math, right? $1.8 billion for exhaustive testing, right? Okay.
For 100 lines of code.
Right? For a few hundred lines of code, right? But the consequence of failure is rather severe, right? You can't put a price on that, right? So the challenge for a tester is, can you validate the software at less cost, but yet have a high degree of confidence, right, that you're covering the most likely situations that would precipitate failure, right? 2 covering array perhaps, 3 covering array maybe a 6 covering array. Let's do a demo. Any questions so far? Okay. So, I just want you to bear this in mind. 460,800 test cases for exhaustive testing. Right? We want to do a few less than that. Okay.
What's the lower bound?
2 covering. What do you think is a lower bound? Right? Shall I look at the... That's a specification
of each of the weeks.
The 2 largest is a lower bound. Can't be less than 100. Right, otherwise, it's not a covering array. Right? That's a proof. Right? You see? If it's a 3 covering, it's 400. Can't be done in less than 400. Right? Because when you rank the levels, there are 2 10s and 1 4. So it's 400. Can't be less than 400. It was a problem similar to this, by the way, that I had to explain to someone that they had a case, right, where they said, where the lower bound was, I think, 380 something. And they claimed that they were getting 2 covering in 350. Can't do it. Right. Okay.
For you?
Okay. That's right. Okay. Okay. So I'm going to do some magic here. Rather than entering in all the factors, I'm just going to load them. It's pretty cool, huh? I predefined them and just loaded them. How did it know where to load them from? Well, No. Actually, it's a pretty cool thing for our platforms, right? It checked to see it checked the environment to see if there was a construct that had a keyword in it that said this is a factor table, and it said if you're loading factors, those must be the ones you want. And so I just predefined it beforehand. Okay. All right. So let me just back up a little bit. Notice the strength 2. We know the lower bound is 100. Question is, can you construct this in 100? Because you can't do it less. Right? So let's see. And you can. Right? How do I know that you can? Because by the magic of jump, it tells you that there are 100 rows. And my report tells me that it's a 2 covering array because 100% of 2-factor projections are being covered, 72% of 3-factor projections, and 40% of 4-factor projections. So guess what? If you go to your manager now, right, at the software firm that builds the TCAS system, and you said, you know what? The cost that you guys were negotiating with Congress for was $1.8 billion. I can do it for you in $200,000. Can I have a raise? Right?
Of the difference.
Right?
$500 million should do it.
Right? And I'm not greedy. Right? Just double my pay. Right? And you have ensured that any failure that could be precipitated by 2-way interactions is covered. Okay.
Is the diversity some measure of like how many times each one?
Yes. You know about covering arrays.
Well, I thought I knew that.
That's exactly what it is. Right? It's something that was proposed by Colin Mallows. Right. So I'm going to back up here, and I'm going to say, well, what if your budget? What if your boss says, you know, this 2 covering thing can't possibly be good enough? And you can say, well, give me a few minutes. I'm going to do 3 covering. What's the lower bound? 400 runs. Can you do it in 400 runs? Oh, we don't know. Right? We have to try. Right? This is a harder problem now. Right? We're constructing this thing. We're all possible 3. It's 10. It's 12 choose 3. Right? And we have to construct it. You're shrugging like, how hard could it be? Right? It's going to take a few seconds here. Let's see.
So it's iterative. Like a catalog.
No, what? We'll see. 400 runs. Right? In fact, so if you're to look at the end of the presentation, I'm going to give you examples of tools that exist to construct covering arrays, right? If you're to look at the tools that exist to construct covering arrays, most of them cannot do it in 400 runs. Right? So I have a paper coming out which shows you a theorem on why it can be constructed in 400 runs on not just this one, but problems, right, of a certain specification of 3 covering arrays, what the lower bound, what the it's a upper bound argument that I'm using where the upper bound coincides with the lower bound. Right? Under what conditions does that happen? And it so happens that this problem fits into that category. So is that making sense? Am I making a case that covering arrays are useful things? Yep, okay, all right. Okay. I'm sorry?
Now the budget is it.
Oh, right, no, you should get you go back and you say, no, surely you can give me a raise now. Okay, all right. So I'm going to talk about, so you may say, okay, but can it help me? I don't build TCAS systems and the like, right? I build regular software, right? Like I write Mavericks operating system for the Mac, right? I work on that. Can this help me there? Okay. So I'm making the argument here that users of modern software, right, whether it be a browser-based software or Windows or the Mac, right, you interact with the software by a succession of dialogues, right, where you have checkboxes and off-GUI controls, right? And here's an example from preferences on the Mac, keyboard preferences. See all of those controls. You have to test this stuff, right? And it's not uncommon to have 50 or more controls. Right? Here's another example. This is text import for jump. Right? All of these controls. And this is going to make you take a This is a preferences system for the least squares platform in jump. Right? Regression, right? There are 56 checkboxes here. This is one platform. The user can set these things to make jump least squares, customize it however they want. Right? I want this to show up on the report when you analyze your data. I don't want it to show up. And on and on and on, 56 choices. And this exists for every single platform in jump, and somebody has to test it. So, if exhaustive testing was done on just this, assuming you could automate it and do 1 million test cases, right, per second, it would take 2,285 years. And we release a version of jump every 18 months. Hold on, don't use the preferences yet. Wait until jump 2010, 9,036. And you're right. And then you tell the user, it doesn't work. I've waited for 9,000 releases and you can't use it because now I have to go fix it. And it's going to be another 2,000 years before you know whether or not my fix works. Right. Okay. So this is not practical, right? You can't do this. Okay.
Change the window.
Right. So you have a few options. Come up with a better testing strategy or get rid of this stuff. Right? Okay. So you can actually test this in 9 test cases. 2 covering array. Do you want to see?
56.
factors.
56 booleans.
56 booleans. They're all checkboxes. It's either checked or unchecked. Right? 56 factors. 2 to the 56 exhaustive testing. If I'm saying 2 covering all possible two-way interactions, I have asserted that failures will not be due to 2-factor interactions. I only need 9 test cases. That is amazing. Shall I show you? Just in case I'm making it up. No. Okay. This will be quick. I'm almost done. I will be done by 8. So all we need to do here is put 56 in here. Right? 2 level. Continue. Make table. 9 runs. See how fast it is?
Well,
Right?
because we know the 2-2.
Because what?
Because we already solved for
Right. Right, because it's solved. It's a solved problem, right? But what is not solved is a related problem. What if I did this? That is not solved. Right?
And there's no like closed form solution for even how big we should expect that table to be?
None. Not for this problem.
So this is why we need this to go like graduate school.
Right. Right. You can go solve this problem. Right. Right. In fact, what is known, I've constructed it in 34 runs like that, but I know that it can be smaller because I know that Charles Coburn at Arizona State has done it for 30 runs. So I'm a little bit peeved by that.
So basically just, your algorithm is just kind of like, there's a search.
No, my algorithm is not a search. It's what is called a mathematical construction, right? It's a recursive, this is what is called a block recursive mathematical construction, right? Which is why it's so fast, right? So there are search-based algorithms, but they're slower than this.
Right, so you're still trying to figure out how to get down to 30.
Right.
Because there's no definitive way to determine how to
Right.
So you have to run the thing.
Right. So I know that with my algorithm I get 34. Right. I also have an optimize feature, what is called a post-construction optimizer. Right. But it actually, I'm not going to run it because it's the time complexity of my optimizer is severe. Right. So it will make it smaller. Right. But you guys have other things to do tonight.
But you know that there's no duplicates in that row, the list of 34. You're just basically saying
Right. In this construction, I know that there are no 2 rows that are exactly the same.
Right.
Now, there's this notion of identical rows, right? Yeah, so an identical row is a little bit different than what you're saying. There are certainly no 2 rows that when I look at it, the settings are the same. Yeah. But it could be that there are certain cells that are what you call the do not care values. Right? It could be either 1 or 2, and you wouldn't change the coverage property. Right? And so there may be 2 rows. That's how I can make it smaller using my optimizer. Because when I compare it, taking that into account, they are identical. Right?
Because you're choosing like 3 rows or 3 columns at a time. So
that's how I know that there are some do not care cells. Right? But we're getting way down into the weeds here of the algorithm. And I'll happily talk to you about that afterwards and show you how it works.
But you know that you cannot take a row out.
I know I can't take, right. This one here. This one here. If I were to take a row out of this one, it wouldn't be covering. Right? But I can optimize it. Right? I can examine it, see if there are rows that I can merge, and I could reduce the number of runs. Right?
So it's minimal.
Right. So, right. This is right. This one can be made smaller.
So, could you address the interpretation now? For example, if the 3rd row fails, you're fairly clueless as to why.
Why do you? Okay, that's the problem that I wasn't going to talk about.
Well,
but
put it this way, you're much more clueless than if you had an orthogonal. But how clueless are you?
So perhaps the question you're asking, right, is a diagnostic question. if I go through these and I observe a failure on a particular run, is there some way for me to know what factors precipitated that failure? Is that the question you're asking? And guess what? There is. I have a script. Well, I shouldn't say I have a script, but that's a problem that I'm working on, right? And I could actually show you the way in which I do this, right? So you can narrow them down, right? You may not be able to say that these two factors did it, but I may be able to say that it could be this factor and this factor and this factor, right? And those are the ones you need to look at, right? Yeah? That is a really useful thing. Because imagine that I have 100 factors and there's a failure. Oh, God, how do I know? Where do I start? I need some mechanism to help me to focus in on the factors that precipitated the failure, right? And that's an active area of research when you go back to graduate school. That's a dissertation. Right? Okay? There are many ideas about that, and the idea that I have two different. Myself and a colleague, we're writing a paper on one way, but we can talk about that later. Okay. Shall I continue? Any more questions, or shall I just go ahead?
Do you have any examples of how little or how much you could narrow such a thing? I know it's hard to say in general, but...
Well, it depends on where the failure is and how many failures there are, right? Yeah. There's information, if I have 9 runs, right, and the failure occurs, you see, if you think about it, right, it's a covering array, and if the failure appears on, say, the first run, right, then I know from that first run, let's say it appeared in the second run, right, not the first run, appears in the second run, then the first run has K choose T tuples, right, that did not precipitate that failure, right? So I can use that information in conjunction with the information on the second run to isolate factors. And if I continue doing that through all the runs, then I may be able to narrow it down to perhaps just 2 factors. It really depends on what runs the failure occurred.
So is it set up the way that you have to run all of them and afterwards you can do that diagnostic to narrow?
No, you don't have to. Right, the way in which it does it, it says, what I do is, when I construct it, I create a column, which is called a pass-fail column. And as you're testing, you just say pass, fail, pass, fail. And the diagnostic tool looks at the pass-fail column, looks at the settings, and figures out what factors could have precipitated it.
Do you have to have done all the runs?
No, because it's just looking at pass-fail. Right? It's pass-fail and missing. So missing has no information in it. Right.
When you're done the first run, you know that, and then that passed.
Right.
You know, A1 equals 1, A equals 1, and B equals 1. Right. Doesn't fail.
Right.
You know, A equals 1 and C equals 1.
Exactly.
You know all those things.
Exactly. So you have that information that you can use in conjunction with the passes to know what could have precipitated the failure. So you don't have to do all of them. Right? It just examines the ones that you have already done. Okay. All right. So I don't have much time, but there is also this issue. I'm not going to bother to do the demo here, and these are just 2 slides. This is, in the real world, there are additional complications, right? Right? Your question was, well, not all factors have the same number of levels. Another question is, well, there are factors where, or are columns in this in this world where a setting of a particular column or factor precludes settings of other columns. That is what you would call a constraint. That is the real world. Most software is like that. Right? I check this checkbox and it grays out all of these checkboxes. Right? Now, if you want to write a dissertation, go at it. This is a not completely open, lots of people have done work, but there's a lot more work to be done in this area, right? And so I can give you a demo, but I'm going to skip it unless you really want it. Colin, and so I have some definitions here and some notation that I came up with. And the network interface testing problem is a problem that, when I was a PhD student and I presented my first paper at a conference called the International Symposium on Software Reliability Engineering, right? And there were some guys by the name of Williams and Probert that presented this example at that conference, right? And so that was the example I was going to do. They're from AT&T Bell Labs, and it has to do with telephone switches, right? And I'm going to just show you the example because it dates it, right? So look at the originating phone type. One setting is coin, right? When was the last time anybody saw a payphone that uses coins? Right, but I'm going to pass on this, okay? And go to this slide where I give you some sense of the tools that exist. Okay? The tools, there are many tools that exist. Some are free, some are rather expensive, right? AETG is perhaps the oldest tool that's been around for a really long time, right? It used to be state of the art, right? And it's probably being eclipsed by a tool that is available from NIST now, the ACTS tool, right? Hexawise is run by a local guy, and it's free for certain organizations, but when you go to their web page and you look at the prices, there's a $50,000 charge, and I'm not sure exactly what that is for. I don't know if you get source code or something, I'm not sure. But there are lots of tools that exist for this, right? So that's just to give you an idea if you're interested, you want to learn more, right? And so here are some takeaways, right? So I touched on the first one. Empirical research suggests that most software failures are due to faults resulting from the interaction of few parameters, typically fewer than 6, right? The NIST guys have written several papers on this, right? So test case selection based on covering arrays. The term combinatorial testing is a phrase that you will see. They're talking about the same thing. Can exercise all T-way combinations at very little cost. Compared to exhaustive testing, the cost savings is dramatic with potentially very little impact on quality, right? So you're giving something up. But as Dan pointed out, for foo, the probability that a failure is due to 4 is perhaps very low, right? Okay. So some research that I've done many, many years ago was on this business of fault detection effectiveness, where I was looking at things like code coverage and the relationship between code coverage and fault detection effectiveness, right? And as it turns out, research going on now says that test cases derived from covering arrays result in high code coverage, right? And hence exhibit high fault detection effectiveness. Stands to reason when you think of what they are, right? And real world challenges like constraints can be handled as well. And that's it. Any questions?
It looked like you were planning this for Jump 12.
Well, I'm not allowed to talk about what is coming out in new features in Jump. But if you think this is cool and you want it to be in Jump 12, I think you should send Melinda or me email and we can persuade our managers to make sure that it happens. Is that the right answer?
You played this game all the time. You should send it to Joseph.
Right. So I've been doing work in this area for a very long time. We use covering arrays at SAS to validate our software, right? We've certainly used it in Jump for a while. And if there is the desire in the community of Jump users for this, we can make it happen.
It's an interesting idea, testing your own software.
We eat our own dog food, right? And in fact, it's not just Jump. If those of you who know the name Warren Kufeld, right? Warren Kufeld, before I went to the Jump group, I worked in a group at SAS called Advanced Analytics. And Warren Kufeld works in advanced analytics and is this iconic figure in the choice experiments field and in orthogonal arrays. He maintains this library of orthogonal arrays. And one of the things we did, and what we did together, is we became advocates jointly of covering arrays for testing. So if you are a SAS programmer, you know what a proc is, right? For testing procs and so on, right? So that's what advanced analytics does. Those people write the procs, right? So Warren Kufeld has a set of macros that he has a hidden option that will construct covering arrays with some caveats. And if you're interested, I can tell you what the caveats are. Yes. right.
I was a MarkTex evangelist. I traveled the country for about 5 years.
Is that right? So they can now, but they are. You need to know macro programming. Right. And you know his algorithms are search based, right?
Yeah.
So it can be very slow and it may not find a covering array, right? So it's not intended to be marketed as a tool to construct covering arrays in general. It's intended for internal use, right?
I won't tell anybody.
So don't tell anybody, right? So Warren Kufeld and I sort of collaborated on this.
I actually have what are bad uses for covering arrays? So we talked about some really great places where covering arrays are a really good idea.
Mm-hmm.
Where does this not work? What are the types of scenarios?
Right. So there are lots of places where. So before I answer that question, I wouldn't want you to leave this room thinking that the only value in covering arrays is for software testing, right? So covering arrays existed long before software testers sort of grabbed this opportunity, right? Comes out of the discrete math community. It's also good for what is known as configuration testing, right? So imagine you're building products, right, that you have to configure, right? It has to run on this platform, and it has to have this going on, and it has to have this piece running, and there are many combinations. Think of any modern software system that may have to run on multiple operating systems, Windows and Mac, right? It's browser-based. It has to use all of these browsers, right? That is configuration testing. Very, very, very useful for configuration testing. Now think of the kind of software that you have, right, to get to your question, where you have like drag and drop operations, right? Not so easy to use covering arrays there, right? Specifying the factors there is non-trivial, right? So when you're talking about GUI-based software where you have checkboxes and controls like that, natural place. Talking about functions where you have arguments, natural place, right? When you talk about these sort of like in Graph Builder, right, not such a good place. It's not that it cannot work, but the work involved, right? I should point out that the construction of the covering array, although non-trivial, is not the hardest part. The hardest part is the design work. What are the factors and what are the levels? Right? Like in any design of experiments problem, that's where you do your work, right? And so there are problems where that aspect of the work is considerably harder, right, than in a simple GUI interface that has checkboxes and combo boxes and so on. Does that answer it a little bit? Any other questions?
Well, let's thank the speaker.